In this video, we are going to look at some of the basics surrounding tangent lines, tangents to a curve, and also velocity problems. These two are related because when we look at a tangent, we're honing in on how fast something is moving at a particular moment in time. Let's start with a little bit of background information. Um, just sort of to remind you about the algebra behind finding the slope for an equation of a line, looking at the rise over the run, right? The difference in the y values being the rise, and the difference in the x values being the run, right? We use this notation with a sub number, the number that's just below the variable. This is y sub 2 and this is y sub 1, just to denote that we're talking about two different y values because we're looking at two different points. That algebra is extending itself into calculus now because we're going to start talking about what's called a secant line. The secant line is one that connects two points together. The line is right here. And you can see that it is connecting two points that are on the curve in this particular case. A and B are two numbers that have been plugged into the function. And when we plug them in, we have their output values. When I plug A in, I get the output value of f of A. And when I plug B in, I get the output value of f of B. So again, these 2 points that I see on the graph are, this is B comma f of B. Those are the coordinates of that point. And the point down here is A comma f of A. So extending the idea that we have from above there of finding the slope of this tangent line, we're finding the difference in the y values, that's going to be this part, versus the difference in the x values, which is this part. So this is just a more formal definition of finding a slope, or what we're calling the average rate of change. The reason we're calling it a rate of change is because if I were to pick two different points, let's say I picked a point here and I picked a point here, and if I were to draw a line between these two new points, the line that I get is going to be at a different slope than the one that I had drawn before, right? Let's do that. Let's look at those two in comparison. So here's a different line. The slopes of those are different. And so we want to talk about how those slopes changing over time average out. This is just kind of putting together what we were saying more formally, but also taking into account now that rather than taking two particular points, let's say A and B, we're going to start with only one. We're going to start with a point A. And we're going to have some arbitrary value h that we've added to A. So this new point over here on the right is a distance of h away from that original point A. When we plug those two into the function, their output is f of A. So here's the first point. And then the other one is the x value is A plus h. I started at A. I added h to it, so here's my new x coordinate. I'm plugging that into the function, and my y coordinate is this, f of A plus h. This is the more formal way that we talk about slope in calculus, extending from those x and y variables that we had on the slide before. And what we're eventually going to be doing is we're going to take this distance h and we're going to move it closer and closer to that original point A. We're going to, instead of have it where it started here, we're going to maybe move it here, and then maybe move it here, maybe move it here. So what we're essentially doing is taking the distance h and we're shrinking it down to 0. That's where this part comes in. Limit. If I were to get very, very close, if those 2 points would be very close together, I'm approaching this limit. I never get right exactly to it. I don't want A and H to be the same, right? Because then there's no distance between them. But in theory, I want them to be the same so I can figure out what's happening at that particular point in time. This week, we're talking about tangent lines and secant lines and how they relate to one another as far as their change. And then we'll be moving forward thinking about limits in the next week. So here's a function. Let's consider the function x squared plus or minus 5, just a simple parabola. And we want to find the average rate of change on a particular interval. So what this is saying is I'm giving you two x values. The first x value is 1. The second x value is 5. If I plug those into the original function here, if I plug 1 in, I get -4. So you can see I've got the point 1, -4 here. If I plug 5 into the original function, I'll get 20. So here's another point, 5, 20. And to find the average rate of change, what we're really doing is just finding the slope of the line between those 2 points. That's all that it's asking us to do. So, hang on, let me make a little space here. So for this first example, I think that the average rate of change the change in y over the change in x is going to be 20 minus a -4, right? And then a 5 minus 1. So in this particular case, we're getting, what's that, 24 over 4 or 6. Looking at that line, I can see it does look like the slope of that line is 6. It's pretty steep and it's positive, right? Here's another example, zoomed in, same exact function, but zoomed in. In this case, we're going between the points 1 and 2 instead of 1 and 5. So we're in this part of the graph instead. Looking at the graph on the left, now we're going to this part of the graph, right? Just a smaller portion of it. Again, we plug those points 1 and 2 into the original function. So what I mean by that is I'm saying, okay, well, what is f of 1? I'm going to get 1 squared minus 5. So it's going to be -4. What is f of 2? Plug that into the original function. I get 4 minus 5, which is a -1. So that's the 2 points that you see here on the graph. And the average rate of change is going to be the slope between those 2 points. So the average rate of change, just abbreviating it there, will be the y values. Let's see, we'll have a -1 minus a -4 over 2 minus 1. So that's going to be 3 over 1 or 3, right? Not too difficult. We're just finding the slope between 2 points. But again, our goal is to work towards a tangent where we're touching the graph in exactly only one point at a time. What we're going to start doing is, going back up to the slide before, we're going to take this secondary point, I'm looking at the graph here on the left, and we're going to systematically move it closer and closer to the first point so that it ends up being really, really close to it, right next to it in very, very small differences. So that eventually we're at a single point of intersection, which is called the tangent. In this particular first picture, we are touching the curve in only one place. In the second one, the graph is touching that particular line in multiple locations, but it still acts as a tangent because at the point P right here, it's only touching the graph at one point. So where it intersects the graph in another portion doesn't really matter. We're only looking at a particular point one at a time. Here is a parabola, just simple, x squared. And we want to find the equation of the line that is tangent at the point 1, 1. Well, what we were working on before was finding the secant line, right? Just drawing a graph here, a larger, sort of blowing this graph up. I have a point P, it's at 1, 1. And what we were just doing was taking another point somewhere up here, drawing a line between them, and then we were able to find the slope. To find the equation of a line, we need a point. We have a point. We've been given that here. And we need a slope. Well, looking at this line, if it's only crossing in one place, how do we find the slope? Well, we're going to do that by approximating. Now, this is something that we used to do, by hand back in the day when I was in school in the dark ages. But now we have computers to kind of help us. So this is just calculations that are done for us. What I'm doing is I'm trying to close in on the point 1, and I'm coming from the left side and from the right side. So on the number line, I'm closing in on x equals 1. And so this table on the left started at x equals 2, and then chose points that are closer and closer and closer to 1, right? That's what we see here in this column. We're getting closer and closer to 1, but not sitting right on top of it. And the second column is plugging these values into the function x squared, and this is what we're getting as our output. Or no, sorry, we're plugging it into the secant line. We're finding the slope of the secant line. So m between p and q, going back up here, this point here is q, right? So for the first example, we're starting at 2, maybe, and then we're moving closer and closer and closer in this, and we're finding that slope. So when I look at the points between x equals 1 and x equals 2, the slope there between them is going to be 3. When I look at the points x equals 1 and x equals 1.5, the slope there is going to be 2.5. So coming from the right-hand side, it looks as though we're closing in on the slope being 2. Similarly, if I look at the table on the right, I'm going from the left-hand side. I'm starting at x equals 0, and I'm choosing points that are closer and closer and closer to 1, approaching from the right. And again, similarly, we're looking at the slope between those 2 points. When x equals 0 and x equals 1, the slope between those 2 points is going to give us 1, and so forth. Looking at this from both sides, I feel comfortable making the conclusion that the slope is approaching 2. Here's a picture of what's happening. The pictures on the top are showing us the tangent lines as we move Q, which is the secondary point, closer and closer to P. And we can see how the slope of the tangent line is changing, right? And then the pictures down here at the bottom are starting from the left-hand side. We're starting with the point Q, moving closer and closer to P, and how those tangent lines are also changing. Just to kind of overemphasize this, we have a tangent line like this, and then it goes like this, and then it's going like this. It's kind of leveling off, right? From the other side, we're going like this, and we're going like this, and we're going like this. We're ending up, that last one's no good, like this. They're sort of changing, and eventually I have these two that are kind of similar, right? And that's right at the point of tangency. So if we wanted to find the equation of the line that's tangent at that point, we would say, okay, the point was 1, 1. Remember, the function was x squared. And we said that the slope was 2. We use this formula, y minus y1 equals mx minus x sub 1. This is the formula that you use when you have a point and you have a slope. So I'd say y minus 1, taking the y coordinate here, equals, well, we said that the slope is going to be 2. We found that just to see what the limiting function was. And this is x minus 1. So y minus 1 equals 2x minus 2, or y equals 2x minus 1. Pause for a second. So I wanted to pause for just a second because I wanted to switch over to Desmos. So we can see I just graphed x squared, which is the graph we were looking at. And then I graphed the line that we found, 2x minus 1. And I can see that at the point x equals 1, let me plot the point 1, comma 1. Right there, I can see zooming in that, yeah, that does in fact look like it's a tangent line. Right? And we can't zoom in far enough, but we can see that blue line appears to be intersecting with the red graph, kind of hard to see because I've zoomed in so far here, in exactly 1 point. So just wanted to verify that the answer that we got does make sense based on the graph that we're talking about. Is an application of this particular idea. Suppose that a ball is dropped from the upper deck of a tower in Toronto. I think it's supposed to be the CNN tower. I think that's a typo there, which is 450 meters above the ground. Find the velocity of the ball after 5 seconds. So part of what we know now from experiments that happened long ago from Galileo is that he was able to predict the speed at which an object will fall based on gravity. And so we have this nice equation here, right? We're just taking that 4.9 is taking the gravitational pull into account. So S is going to be the distance, and T is going to be the amount of time from when the object is dropped. It's difficult to find the velocity after 5 seconds because we're dealing with a single instant in time. And in this case, no interval was given to us. Like what we were doing before, we're trying to find what's happening at an exact instant, not the difference between 2 points. But we can approximate by computing the velocity over a brief period of time. In this case, we're looking at t equals 5 and t equals 5.1 seconds. So starting at 6 and looking at the interval between 5 and 6, we can figure out that the average velocity is 53.9 minutes per second. Again, what we're doing is we're taking that function we have up here, s of t equals 4.9 t squared. That's the function that we're taking. We're plugging in t equals 5 and we're plugging in t equals 6, getting those output values and finding the slope between those 2 points. And then we repeat the process for 5 and 5.1, right? Closing in, getting closer and closer to 5. And by looking at the right column, it looks as though the velocity is closing in on 49 minutes per second. And so we would say that the instantaneous velocity at that particular point, right when t is equal to 5 seconds, that the object is moving at 49 meters per second. We're going to talk about a lot more examples like this in class, and so bring lots of questions. Have a great day.